During lunch, I was chatting with people and realized maybe there's certain non-intuitiveness about vision, yeah, or in fact about our brain. And so when you study the universe, you can put yourself away from the universe as if you're outside the system, and you study the universe. But now we study this universe subjectively, no? Because we're studying ourselves, where observers is inside the system, a scientist. And so therefore, often in studying the brain, there is this counterintuitiveness. Okay, and that kind of interferes with our scientific investigation. So for example, one of the counterintuitiveness is you think that if you have already sampled everything on your retina, you already see it. Yeah? Unless you're blind, maybe your retina has some disease. So somehow it's not counterintuitive that after encoding, there is selection and there is decoding. Okay? So far today is the last lecture of encoding. It is still a camera with some microprocessor. Well, actually today we're going to start going to V1. Okay, V1 you start to encounter problems. So therefore, this non-intuitive. Let me just tell you an interesting episode. So in 1960s, when computers start to get more advanced, people can start to programming, and so therefore, anything you want to do, you just say if, then, for this, loop and all these kind of write it down. You can make automated calculation steps. And then a group of people at MIT thought, vision is just like that. You give an input that's an image, you do a few calculation steps, then you can say, oh, here's a dog, here's a cat. Okay, that will be an output of a program. And they thought this is such a simple computer programming job that they think this can be done by a summer undergraduate student in one summer. Okay, that's how counterintuitive it appears to us. Yeah? It's like, oh, how do you write a computer program to do multiplication of two numbers? Oh, you can write a computer program for that. And write a computer program to input as an image, output and label as a cat and dog. It's just a little bit more complicated, but it's just a computer program. So that was so counterintuitive. It was thought like a summer project. And of course, the summer project lasts for decades. It didn't quite get finished. And then PhD student got in, professors got in, and the whole world got in, whole world of computer vision researchers got in and just could not do it. Yeah, and so that is the trouble. But we will encounter that. So just to let you know, so far we are still at the encoding stage. Starting from tomorrow, we will get into this counterintuitiveness and the difficulties as a scientist to study this problem. And that makes it even more difficult to pose what is the question, okay? So that's a light beginning, and so let's see where we are. We have looked at this efficient coding theory, look at the original sampling at the sensors, sensors sensitivity, sensors spatial distribution, sensors sensing on the light spectrum, and so on. Then after the sensors, we focused on how to transform the censored information into a neuron's firing in the next stage. And we saw that it was really powerful to understand the retina coding in space, retina coding in color, the retina coding in time, okay? And then, in fact, in the beginning, we dealt with something about coding two eyes, okay? Coding two eyes is not on the retina because each retina is just one eye, okay? So another retina is another eye, so coding two eyes together, if you combine them, is actually in the first stage of the brain when the eye signal downloaded into brain to combine. Okay, so now we wonder, you can ask this question, how far can the efficient coding go to explain visual processing in our brain? And we have already dealt with one aspect of it when combining the two eyes. Let's look further, okay? Where is the limit? So, just to review for ourselves, this is a particular formulation of linear encoding by changing the input, by encoding the input signal S to output O by a linear matrix. And we realized that we have used this magic analytical solution successfully in the retina. However, the retina, the two eyes, they go to the brain into V1, and that's where they start to mix. So left and right eyes mixed, but let's forget about that. They're actually two half. But anyway, they mixed. And the retinal resistive field no longer looks like a center surround resistive field that yesterday we derived. It looks like this, okay? It can be oriented as a horizontal thing, and for instance, this particular resistive field, if you give it a horizontal input, it will be excited. This is part of your homework on Monday, yeah? If you tried it. And then, it gets excited when some bright pixel in this region, some black pixel in this region. If the pixel has these kind of arrangement, on its resistive field, this neuron will be excited. And then neuroscientists think, oh, this can be built by tiling up these three retinal resistive field array that way. Okay, this is a little bit like thinking about, as an engineer, how can it build? But now let's think about, can it be built like that, okay? And then you're trying to look in the V1, which is called primary visual cortex V1. You find the resistive field may not be just oriented horizontally. It can be oriented vertically, okay? It may not be oriented vertically in this way that, the bright pixel in the center and dark pixel in the surround. It could be bright and dark, they're kind of equal, symmetric, odd symmetric way. And it may be even tilted in a different direction. And it may have a different size. Okay, some are bigger, some smaller. And so therefore, let's ask the question, because there can be different type. The question is, where does that come from? Is that because, remember, we have this degeneracy in solution, yeah? And this degeneracy solution is, in the retina, we chose a particular solution U, which is the inverse Fourier transform of the original decorrelation matrix. So could we reach a different solution, maybe, yeah, in the cortex by a different U? So that could be the first question, okay? Because after all, the original input still has the same statistics in terms of, correlation matrix for different pixels. And so that's the question. So let's recall ourselves. Let's recall that this particular inverse transform matrix looked like this for the retina encoding, yeah? And so it has different frequencies for different columns, frequency 1, frequency 2, and so on. And within a frequency, it has different spatial locations, 1, 2, 3, 4, 5, and so therefore, it's fantastic matrix. But what if we choose one particular U matrix that's just identity? Remember yesterday we talked about, what about identity matrix? Well, still efficient. What kind of resistive field would you have? We mentioned without showing it, but anyway, resistive field will be like that, okay? Because more or less you have a resistive field like that. And what is that? That's a gain on the Fourier wave. As a Fourier wave is like that, therefore a particular Fourier wave of frequency k, you give it a gain. And that will be your resistive field, okay? But here is all of these resistive fields are weighted by these different factors, and you add it together, that will be that resistive field, okay? So remember that resistive field took the form of center surround shape because it is a weighted summation of this kind of resistive field. What are they? This kind of resistive field is a whole Fourier wave covering the whole space, whole image space, yeah? And for different frequencies, it's a different wave. Another frequency, another wave. And so one neuron have this, one neuron have that, and if you add it together by this weighted sum, you get your center surround resistive field, okay? So let's look at that property. This property, these kind of resistive fields satisfy scale invariance, a symmetry that we might like, okay? So when I look at your face, you are the same person, But if you walk closer, suddenly your image on my retina expanded, yeah? I cannot say that you are a different person. So my recognition needs to have the scale invariance built in. So imagine that as you walk over towards me, when you're far, your image on my retina looks like this. When you're near, your image on my retina looks like that. And then it will just simply shift to different neurons and still kind of okay, some kind of thing. So you think that this might implement scale invariance very well. While these kind of resistive fields, remember yesterday we talked about their convolution filters and stuff, they are the same resistive field for each neuron that shift around, and that will give you translation invariance. So that means your face looks like you, but if you walk to a different location, exactly the same size, I should still recognize you as the same person, not a different person. Okay, the same face just shifted. And so therefore, you can imagine this is an extreme case of translation invariance, and this is an extreme case of scale invariance. But actually, in your real vision, you actually want both. Not only you walk around translation, I see you the same person. You walk in depth, I will still see you the same person. Can you make a U matrix that combine them together? Because it appears like in V1, you have these kind of resistive field of different scale. Isn't that for scale invariance? Yeah? So that's a kind of natural question to ask. Could you do that? And yeah, you can actually mathematically try to do that. It's almost like trying to do group theory a little bit. So you have a U matrix that is actually made of block diagonal matrix, okay? And so this block diagonal matrix, for different blocks, each block is a submatrix. And it's just like this diagonal matrix, no? It's just another case of diagonal matrix. So this is trying to do different scales, okay? So this is one scale, this is another scale, this is another scale, okay? While here, you are integrating all scales for each neuron. For each neuron, you're integrating all frequencies, yeah? So all frequencies. But here, for each neuron, you're only integrating a range of frequency in a particular scale, okay? So here is all frequency. This just have a small range. So you have the highest frequency and the lowest frequency, or lowest frequency to higher frequency within this range, okay? And so therefore, you have a particular bandwidth of your frequency, yeah? So, but anyway, if you go through this mathematics, mathematically, you can find it in the, I suspect it's not even in the video that clearly presented a bit more detail, but mathematically you can find it in a book. And just let you know that turns out that maybe because ICTP or whatever has subscription, you can download chapters of this for free from Oxford University Press. Yeah, so you can find it in the book. So in any case, this is like you remember we have this contrast sensitivity curve, which looks like that. When you break it down into different frequency band, it's as if you are, for each neuron, it just looks as a narrow band of frequency. That's what it is, okay? And another band is, the larger scale, because remember, lower frequency, larger scale, higher frequency, smaller scale. And this is what V1 appears to be doing. And this is the reason why you have some neurons have smaller field, some neurons have larger field. Okay? Okay.
How did we even figure out what those receptive fields look like?
Say it again?
How did we figure out how those
receptive fields look like? This is experimentally measured. Remember that experimentalists put the electrode to a neuron and show different images on the screen to see what images make neuron fire. And they realize this image make one neuron fire and this image make another neuron fire. Remember that? On Monday.
Why do we really have these patterns? I mean, like, why there aren't some neurons just scattered all around the V1 area?
So first of all, you ask me what, then you ask why. Why is what we're trying to do. So why is because of efficient coding. Yeah. What is the experimental question? You go measure it. And they measure it by sticking an electrode to to the eye, or to you can stick electrode to the retina, so to one retinal ganglion cell. You can also stick an electrode to the brain, to one V1 neuron, and then you can present different dots on the screen. You find out, oh, if I put a bright dot here, this neuron fire. Put a dark dot here, the neuron fire. But if I put both the bright and dark dot there, that even fires more. Yeah, and then they find this combination, bright and white, on the screen at exactly this residual position, this neuron fire.
So
that's the measurement.
So these patterns are made by like finding some form of correlation between the data that you have given to the eye and what you have received from the.
Exactly. So they say, what correlates the firing with the pattern? And they do it again and again, and they find this neuron, this pattern, this neuron, that pattern. Yeah, very good. Okay, so that's the what question. And now we ask the why question theoretically. Why should it be? Then we say, well, it's perhaps trying to do this kind of efficient coding, trying to get most information while the minimum cost. And then turns out the solution is degenerate and looks like in retina, it's trying to make a solution where all the rest of the field are the same, but they just shifted in space. Maybe in the cortex, it needs to do something intelligent and to recognize a person, not just transmitting information. And recognizing person, we require translation scale invariance. And maybe that's what it's trying to do. And then you're trying to say, if that's the case, can we still at the same time satisfy efficient coding, which does not have scale translation invariance as its goal? Yeah? However, because it has a degeneracy in its solution, can we explore this degeneration in the solution and still satisfy additional goal, which is translation scale invariance? And yesterday we talked about additional goals for hardware convenience. We want all the rest of the field the same. Yeah. Okay.
So like in quantum mechanics, we have degeneracy because like our model is not really specific enough, and the more corrections we add to the Hamiltonian, we figure out the degeneracies are actually different stuff. We just didn't see it. So how do we actually figure that out here when we see degeneracies?
Remember, this is part of the solution when we were trying to derive it.
Yeah, I know. Like, if we like, if here we had a Hamiltonian, and then like we add corrections to that Hamiltonian, would we just like lose those degeneracies? Yes.
So, for example, if in this neural cost you add another cost, you say it costs me to make the different residual field different, engineering-wise, then you will remove that degeneracy. Or in this objective function, you add another term, say, I want to have translation in scale invariance. You will also remove this degeneracy. And so you could do that as well. So for the moment, you can imagine that this degeneracy make you think about what other terms you could add in and whether these terms could be useful. Yeah, very good. OK, very good. So then you say, oh, isn't that wonderful? Then it does make sense. Another thing is, you probably heard about wavelet, translation scales. They're all beautiful symmetry and wavelet coding. Fantastic. OK, so this is all very fantastic.
Oh, excuse me.
Yeah.
Each block of matrix is related to one neuron, one special neuron?
Each block of matrix is related to a group of neurons. Just like, remember, originally, here's a block of matrix for the whole retina. And the whole retina has 1 million neurons. And remember, different rows is for different neurons. OK, so the first row.
Is, how you divide this block of matrix? Why this block of matrix have different sizes?
Because you want, so scale invariance means that you want the shape of the residual field exactly the same. It's just scaled up. OK? So therefore, when things scale up, the frequency actually will also increase. Yeah? So imagine you have a shape that looks like, if you have a shape that looks like this, OK? And then you say, I want a shape half the size. OK, what has frequency changed? This frequency may go from 5 to 10. This frequency will go from what? 10 to 20. So the frequency went from difference of 5 to difference 10, yeah? Expand. The frequency range will expand. This is the reason. The frequency range will expand. This is how scale goes. Yeah, very good question. Okay? And so therefore, the frequency, however, if you look at the frequency in terms of the ratio of the highest frequency and lowest frequency, that's constant. This is a constant of a factor 2. And that's why in engineering, they like to look at the bandwidth as a ratio, and that's called octave, okay? So it's a constant. That's why here I put a frequency in log scale, because in log scale, it's constant. But in linear scale, the factor goes boom, yeah? And so here, when I'm writing matrix, it's all in linear scale. Each frequency is counted, yeah? And so therefore, this looks big. But once you go into that, this is already, you see, this is, you know, yesterday when I was doing this, everything is in the log scale. That's why when you go, it's a power law. It looks like linear, but actually it's a power law, yeah? So often, it's good that you mentioned that so I can point this out, okay? Whenever you look at things on the log scale linear, it actually means power law in the real scale, yeah? Okay. And so all of these power laws and this scaling thing is beautiful for translation invariance. Okay, it's a particular invariance. Of course, this power law actually breaks down here, yeah? And this is because if you keep going like that, it is a power law. Very beautiful, okay? And this region is called whitening. Except when you hit the noise, then it will break down. But if we ignore the noisy region, let's say we have a beautiful image without any noise, you can just keep on going. This is indeed a translation scale invariant situation, okay? And within each scale, you have many, many neurons that tie up the whole visual world, okay? And so the idea is you have these, you have each of these reciprocal field shaped like this. But this reciprocal field still have to tie the whole image, okay? And so you can imagine this reciprocal field, you have more neurons in order to tie up the whole image because it's smaller. But this reciprocal field bigger, you have fewer neurons to tie up the whole image because it's bigger, yeah? And this is also reflected here because the smaller scale, because larger frequency, smaller reciprocal field, but we'll have more neurons. Remember, the number of rows is the number of neurons needed, okay? And so more neurons for small scale things and fewer neurons for large scale things. So this, perfect. And in V1, that's indeed the case. Smaller reciprocal field, more of them. Larger reciprocal field, and fewer of them, okay? While in the retina, you can say, just imagine, okay, it's the same reciprocal field, just tie up the whole space. Although I kind of cheated a little bit, okay? Because in the retina, in fact, you do have difference because in terms of sampling. Here we are looking at this as if the retina sample is translation invariant. Okay, let's forget about this detail. Okay, so that's interesting. Wow, it's fantastic. However, I have hidden one thing from you. So far, we still trying to think about this system. Yeah, so let me go. Okay, so far we think about the system, but in fact, in V1, there's something going on like that, okay? So the number of neurons, in fact, is 100 times more than the number of neurons in the retina. So therefore, this last matrix U is not a square matrix. Okay, so let's go back to the original situation where we have the last matrix is a square orthonormal matrix. Okay, so this transformation, you know, from N to N. But in V1, what happens is this transformation from N to 100 times N. So the number of neurons really expand. V1 is the largest visual cortex in the brain. It takes a lot of resources. Okay, the resources in terms of the area of the brain, because the brain uses a lot of power, metabolic energy to the brain. It also takes a lot of power. So you will imagine it's trying to do something must be very expensive. Is it just for efficient coding? That's a very interesting question to ask, okay? So that is a problem. And so this problem Yes, because originally we do this by one resistive field. Now it's tidying up into different scales. Okay, here I'm going to quote somebody who's Shannon, who is the founder, creator of information theory. Based on this, we have our mutual information, Shannon. So Shannon's information theory appeared in 1948, and then everybody jumped into that wagon, everybody trying to measure information capacity here and there. And then he kind of, rather than be excited now, his information theory is very popular, he says something kind of trying to damp people's enthusiasm. He says, it will be all too easy for our somewhat artificial prosperity to collapse overnight when it's realized that the use of a few exciting words like information, entropy, redundancy do not solve all our problems. And so in the sense that maybe here we're encountering one of these situations, okay? And so why is this expanding, okay? Here I try to make it expand as if I'm just cutting different scales. But in fact, frequency is a two-dimensional vector, right? Remember we said it's a horizontal frequency, vertical frequency. So you can have horizontal wave, vertical wave, and oblique wave, all kinds of waves, yeah? And so therefore, in fact, you don't just carve a frequency in its magnitude. You are carving this two-dimensional frequency space by all of these envelopes of little things here, there, Everything's still on log. No, this is on log scale, and this is on linear scale. Okay, in log scale, you carve it up by equal octaves. In linear scale, large frequency, small resistive field, huge chunk of frequency. Okay, and oriented differently. And smaller frequency, large resistive field, and so on. Yeah, and the tiny, near zero frequency is not even oriented. So really, the V1 is trying to kind of expand for some reason, yeah? And so the largest frequency is in the end of here for small resistive field, and smallest frequency is near the origin here for smallest frequency for large resistive field. Okay, yeah?
Does this graph on the right always suggest that the neurons see not exact matrices with borders, but the matrices are interfering with each other, and somehow this interference...
You mean these envelopes actually on top of each other, yeah?
Yes.
Yeah, that may be another reason that's expanding, Remember when I was doing that, okay, sorry about this, remember when I was doing that, I tried not to make them overlap with each other. That was actually a mathematical solution where all these translation values are exact, where the frequency is actually sharp bordered like this square matrix. But in V1, you realize they're not that sharp. Okay, it's kind of in real experiment data, it's not that. In fact, if it's sharp, it's a frequency by sharp, you have ringing, and that's not good. It's large resistive field, yeah? Okay, if you don't want ringing, you actually want this Gaussian envelope of frequency, yeah? We have this uncertainty principle, right? Gaussian space in frequency is all Gaussian envelope in space, okay? So that's good to point this out, thank you. And so therefore, we have a problem. So let's just look at, okay. So what is our problem? The problem in understanding V1 solely based on efficient coding is starting to break down, okay? There is no apparent bottleneck after the optic nerve, okay? The bottleneck is not obvious where it is, because the whole reason we want to do this is for data compression. Why do we have a data compression? Because we have a narrow band channel linking the eye to the brain. And this is not a broadband channel, so let's compress the data. But where is another bottleneck? Okay, we're going to talk about where is another bottleneck tomorrow. It's not obvious, but I'll show it tomorrow. But today, it's not quite clear. And there is no quantitative demonstration that V1 significantly improves the coding efficiency after the retina. What that means is, remember, we want to minimize this quantity. what is V1 trying to do if it's already minimized in the retina? Is it minimizing further? Not very obvious, okay? No quantitative demonstration. And this is 100 times as many neurons. What is it? It's highly unlikely that neighboring neurons are more decorrelated in V1 than retina. Remember, we're trying to reach decorrelation or reach redundancy reduction in order to save resources, but it sounds like you're wasting resources if you're trying to do that, yeah? So it's very non-intuitive. And as yet, no reliable measure of the data rate in V1 neuron to show whether or how the cost of having vastly more neurons is justified by improvement on coding efficiency. You say, well, maybe this quantity is reduced by having more neurons. There's no such data. Okay. Worse yet, V1 neurons, they actually are not very purist. They feel like this kind of a linear matrix transform of the original image, because they find something called contextual inferences. And this is in experimental data. Imagine you have one particular field that's only this big, okay, indicated by a dashed line, and this recipient, let's say, prefers a vertical orientation, just like here, vertical orientation, okay? So if you put a bar here on your big screen, this neuron will be excited, okay? And then you can also make sure that if you put bars outside this recipient field, well, by definition, it's outside, it will not be excited, okay? So the response will be 0, and this response, let's say, equal to 1. However, if you put them together, the response is 0.3. That's strange. Why is it not 1 plus 0 equal to 1, no? Well, it turns out that these other neurons, because these bars will excite other neurons whose recipient field at their location, and this neuron talk to each other. So therefore, it's just by this feed-forward matrix is no longer the case. Okay, this is a huge difference. Okay, it's not like a 5% you can do perturbation or something. It is a non-perturbative big difference, yeah? As if they have mutual suppression of each other. But if you make the outside bars not all vertical, they're random, then the suppression is less, huh? It's still not 1 plus 0, but it's like it's a bit higher than that. But if you make the outside horizontally oriented, then it's the least suppression, okay? It's almost 1 plus 0, but not quite. Okay, but if you make the outside all line up, but make the inside bar a bit weaker, okay, this is a bit strong bar, this is a weaker bar, then the response will be more than 1, okay? That means the response will be more than if you don't have the outside bar. So there's something strange going on, okay? And so therefore, all of these things make you wonder, maybe V1 is no longer doing efficient coding, okay? So then people say, maybe because this energy function, this objective function is wrong. And then people trying to say, can we make a different objective function? For example, maybe we don't write mutual information. We write something else which have the same meaning but is different quantity. Or maybe the cost is, this is what people, for instance, they call sparse coding, but actually it's have a very similar meaning. And this, I'm not going to go into the detail, but you can find it in the lectures, in the videos, and in my book, okay? Doesn't just, unless you dramatically, if you just do a little bit modification of exact the form of this and that, doesn't solve the problem. However, let's still try to understand there's certain things in V1 still looks a little bit like, so let's say ignore this part, a 100 times expansion. Let's just focus on that part. Maybe we still learn something, okay? Now, what can we do to focus on that part? Because this part includes this gain function, G. Maybe that gain function can tell us something, right? Okay, so in particular, let's just take a phenomenological model of these recessive field, okay? And this recessive field looks like, by the experimental data, you can try to model it. It looks like as if it's a sinusoidal wave with a particular frequency, with a particular phase. and it is enveloped by a particular Gaussian envelope, because this wave doesn't go forever, yeah? This wave is in a particular region. So therefore, you have a frequency. You also have an amplitude, and this amplitude is probably shaped by that, because this is the envelope, yeah? This amplitude, you know, depending on which frequency. At this frequency, the amplitude is very high. At this frequency, amplitude low. At this frequency, maybe something like that, okay? Can this tell us something? Turns out that it can also tell you something, okay? So yeah, different amplitude, you know, low amplitude, high amplitude, depending on where is your center frequency, let's see, okay? So maybe this amplitude is describable by your center frequency. Okay, that's the idea. So let's try to understand that, okay? And indeed, it can give us quite some understanding. Remember we said that if you, this is the envelope, and then you can carve it up into multiple bands. But if you just look at the color channel, red minus green channel, because it has lower signal power, it will be a low-pass filter. Do you still remember that? Okay. Remember that nobody is nodding, huh? No? You remember that? Yeah, okay. So when a good signal noise, you have this kind of a filter. Poor signal noise will be that kind of filter, yeah? And the color channel is for poor signal, that's why it's like that. So therefore, remember with these kind of filters, for luminous channel, red plus green, it will have this filter. For the red minus green, it's this filter. And remember that in the retina, if we multiplex this channel's resistive field and that channel's resistive field, it will give us this kind of a color retinal ganglion cells. They actually do look like that. Remember that? Okay. But this is when you multiplex this resistive field and that resistive field like that. But now, if you have to carve it up into these things, now it should be this resistive field and that resistive field for this band. Okay? For this band. And so for this band, you have this resistive field for the red plus green, but this is so weak, huh? So therefore, this resistive field is having very weak amplitude, but the color resistive field is stronger, so it has a big amplitude, and you multiplex, you will get this for red, this for green. That's just this kind of resistive field. Okay? And so suddenly, these resistive fields make sense. Even though they are bigger, why are they bigger than the retinal ganglion cell? Why are they bigger? Why are they bigger? Okay? They are bigger because now you are only using low frequency. You are not using the whole band of frequencies, yeah? The frequency is low frequency, they are longer wavelengths, so that's why they are bigger. And a high frequency, shorter wavelength, this resistive field will be smaller and will not be tuned to color at all, because by this frequency, color already cut off. This is all black and white. So you go to V1, you indeed find the resistive field that are small are not sensitive to color. The resistive field that are big, they are sensitive to color. What do I mean by sensitive to color? You give different color input, it responds differently. But resistive field is small, you give different color input, it responds the same.
Yeah. Is this because, like, we just see a very specific, like, we have, like, this visual part that we can see with our eye, and then, like, there are some frequencies and wavelengths we do not see colors anymore? I mean, like, we have this, like, from 400 nanometers till 700 nanometers.
Yes.
And then, like, from then on, we don't see anything anymore.
No, these are all within 400 and to 700. So on the retina, you have cones everywhere. It's sampling all frequencies. However, when resistive field can group cones together to pull, okay? So for instance, this kind of resistive field is grouping red and green cone together. They just add red plus green. They don't care about red minus green. That's what it is.
So, I mean, there are some frequencies we have luminosity, but we don't have color anymore?
That's right. This only has luminosity. But the luminosity is based on colored cones. This luminosity just means it takes the red cone and green cone added together. Remember, the luminosity is red plus green. So you have the original input that is red and green. And they have a correlation matrix that not only you have a red, you have a correlation matrix. And then you need to decorrelate them into red plus green, that's your luminance channel, and red minus green, that's your color channel. The color channel is this one. And the luminance channel is having this kind of a bandpass filter, and the color channel is this. So therefore, at this location, the color channel is gone. Only luminance channels survive. And the luminance channel is looking at red plus green. That means these neurons pull the cones, both red cone and green cone is adding up. Okay? And not because it's outside the wavelength range. It's just, it doesn't, you can show a red input, it will, okay, so here, you will show a red input to the bright spot or green input to the bright spot, this neuron will fire. Okay? But here is this kind of reciprocal field. You show a red input, this neuron will fire. You show a green input at this location, the neuron will stop firing. And outside, you show a green input, this neuron will fire. You show a red input, this neuron stop firing. So this neuron discriminates depending on whether you give a red or green input, and this neuron does not discriminate whether you give red or green input. Okay? Okay.
We have a visible range for the eye.
Yeah.
Like we see red and we don't see infrared anymore. We see ultra.
Yeah.
We see blue, we don't see ultra.
Yeah. Yeah.
And so but when it comes to luminosity, it's like we're summing up green and blue. So we see like a bit of a lower frequency or higher frequency here. So
yeah, summing up all the, just like Isaac Newton, you see the white light is a summation of all light.
Oh, so there is a part that there is a limit that we can understand luminosity with looking at something, but we do not comprehend the color anymore?
That's right. At nighttime, you don't see color. But
So
you still see it bright and dark.
So at nighttime, we kind of have a longer range of frequencies that we can comprehend?
At nighttime, not only you don't see color, you also have your reciprocal field, have a low pass filter, your spatial resolution also go down. That was yesterday's teaching, remember? When it's dark, your reciprocal field will grow bigger. So to grow bigger, in order to sum space to enhance the signal. And you don't see color, it's because you want to sum over cones to enhance the signal. But when you sum over cones, then the difference between cones is lost. Yeah, but if you differ between cones, you get the color. Okay, just like you sum over space, the detailed spatial information is lost. You sum over red and green cone, the difference between color is lost. And that's why these neurons no longer care about difference about color. It's just trying to sum over the. So this is actually interesting information. Because the reciprocal field is so small, the signal is very weak. To overcome this, it has to sum over cones in order to enhance the signal. But here, because the reciprocal field is so big, it can afford to differentiate between cones in order to see the color. So it is a very nice design, yeah? And you can also imagine, this is actually something I'm going to teach later, that when the reciprocal field is very small, it not only sum over cone, it also sum over time. So these reciprocal fields do not respond to fast change in time. So they're not very motion sensitive because the reciprocal field is so small, yeah? And so on and so forth, yeah. Yes? Say it again?
Is this related to color blindness?
No. Color blindness is when you lose a gene for a red cone or blue cone or green cone. Yeah, that's you actually. Most people, color blindness is losing only one gene, so they have two kinds of cones. Very few people has only one gene, only one kind of cones. Yeah. Okay. Okay. So yeah. Any other question? Okay. So then you find that at the high frequencies, the smallest field, these neurons are not sensitive to any color. But at the intermediate frequency, these neurons are sensitive to color and orientation. Remember, the lowest frequency, you don't sensitive to orientation because it's zero frequency. But intermediate, you can be sensitive to orientation, remember? The orientation comes from carving this space. You know, if you carve just in a non-isotropic way, then it will be oriented. Only in the zero frequency, it's isotropic, it will be unoriented. So you have some small minority of neurons that are unoriented. Majority of neurons carve the space in a non-isotropic manner, so it's oriented. So it's very interesting. In V1, it's like a zoo, different kind of a receptive field, and to if you don't have this theoretical guidance, you just feel like you have to memorize them all, yeah? But if you have the theoretical guidance, just by these curves, you can, they are all in the same framework, okay? You can derive them. If you forget, you can derive them, okay? So that's nice. You don't have to like, have to remember everything, okay? But this is the idea. And okay, let's just, for example, look at an example where, for example, at this particular frequency. Okay, let's look at this particular frequency band. For your luminance channel, you have one particular field dictated by this luminance filter. Let's say it corresponds to this black filteristic field, okay? For your chromatic channel, it corresponds to this resistor field, okay? This is your Gabor filter in 1D, just like I plot here. And then you add these together, get that, and that's what you get. So you get a resistive field for your red input and resistive field for your green input in that kind of way. Wow, so this neuron has a very complicated resistive field shape, which is not like red and green like that. So it's in this complicated way. But depending on different phase relationship for your luminance and the chromatic filters, you can have this really zoo of different kind of color resistive field, okay? And this is really, really, it's like if you want to study biology in this way, it is really taxing your memory, yeah? But nevertheless, they just come out from this understanding, okay? So if you add these, just like you add this as, add these, get that, and different this, get that, you will get that. And then it just come out like so. Okay, so a diversity of space color mix of your resistive field. Mix this way, mix that way, mix that way, and within that, it could go different ways. Yeah, and this may be another reason why V1 is 100 times expand in terms of neurons, because it's trying to cover all these little variations, okay? And you can include time, so therefore not only spatial frequency, your temporal frequency, okay? It's good that because you ask that, you can say, okay, on high spatial frequency, resistive field very small. Because the resistive field very small, I cannot afford to have high temporal frequency because otherwise there's no signal left. So on high temporal frequency, usually you focus on low temporal frequency. Things change very, very slowly. You're trying to accumulate through time to boost up your signal so that you can afford to do small spatial details. So whenever you look at a small spatial detail, you better don't move. Okay? If you move, you can't see it. Yeah? Hold still, then you can see the detail. You know? Yeah, this is the idea. If you see something moving, you want to go to slow spatial frequency, very big. The whole thing moving, you can see it. Okay? So you can see this, that these small resistive fields are very insensitive to time, and large resistive fields are very sensitive to time. Moving things have to move, big things to move. Okay? Yeah. So small frequencies go to huge range of temporal frequency. Small spatial frequency, huge range of temporal frequency. And large spatial frequency, small resistive field, focus on low temporal frequency, okay? And then so this is, you know, Small resistive field, large, temporary, not changing. This is time, this is space, okay? Time and space. So maybe this get into too much detail, but I give you these kind of intuition you more or less can feel. So I'm going to jump out. But let's look at stereo vision. Now let's make an analogy between red and green to left and right eye. Okay? So same idea. Just like here, I talk about red and green. They can go to red plus green, red minus green. Left and right eye. Left and right eye add together. Left and right eye subtract from each other. You can get these kind of things. Okay, the neuron prefers the left eye input, but not prefer right eye input, and so on and so forth. Okay, and so you will have V1 neurons mixing not only which eye, but also the resistive field from which eye. Okay, so it could be that it prefers the left eye input at this spatial location, okay, at this spatial, but right eye input at this spatial location. Why are we doing that? This is because in 3D, you are trying to, okay, so let me draw something. This is also in one of the videos for the first day, but I did not dive in detail, so let me just draw it for you. Okay? This is called space. This is how you get 3D space. Imagine you have two eyes, and you are focusing to look at that location. Okay? That means this falling in your left eye exactly to the center of your left eye image, right here. Okay? The center of the left eye image. And you're focusing on that, so therefore, go to right eye, the center of image right there. Okay? So they are exactly in the center of your eye. Now imagine you have something behind. Okay, it's a bit further. Then, let's say they all fall through this pupil. So therefore, to fall through this pupil, it lands here. Now it falls through this pupil, it will land here, no? Okay? And this will fall through this pupil. It will land here, no? Okay? Of course, you know, in the eye, it's the opposite. But anyway, this will be going, yeah. It will be here in the real image. Okay? So therefore, this is a point 1, this is a point 1, and this is point 2. Point 1, they're both in the center of the image. Point 2 is to the left of the image in the right eye, left eye, in the right of the image center in the right eye. And so this point is not exactly the same location on the image. So you better have a V1 cell whose left eye resistive field is right here, whose right eye resistive field is right there. They have to be a bit different, yeah? That's how you can tell the depth. And this is exactly what it is trying to do. The left eye prefers a location at this spatial location, the right eye prefers that spatial location. Do you see what I mean? That's for a point that's far. But if a point near, say, if a point near, you will go like this, you will go like that, and so on. No? This will be another location. So V1 has, so you can imagine for the small resistive field, it cannot tell the eye's difference, but for large resistive field, can tell the eye difference. So V1 neuron with large resistive field, they are also charged in trying to look at 3D. But for small resistive field, it will just add two eyes in order to boost the signal. Okay? This will all come out like that. And then indeed, that's the case. You can go look at in V1, that's indeed the case. In fact, this is the prediction for my theory. People, I'm not sure whether they actually looked that closely, but I looked at it and that's still the case. Okay, I'm not going to dive into the details for this. So, I'm sorry, why is this? Maybe it's an emergency. What's going on? Yeah, sorry. So, okay, so we now see that. Let's also remember we look at the space separately, time separately, and we're starting to look at color and space together, disparity and space together, and space and time together. Then you say you always only look at two things together. How about three things together? How about time and space and color? Yeah, because after all. And how about time and space and color and about two eyes? 4 dimension. Because after all, our input is 4-dimensional. Yeah. So combining 3 or 4 feature dimensions. So spatial feature, temporal feature, color feature, and ocular feature, yeah? So you can say, okay, space-time, let's say for one axis, for small frequency, it's for large resonant fields, small, slow-changing things, and large frequency, small resonant field, fast-changing things, okay? Similarly, for color, okay, here is where you add color cones together to make it just bright and white, okay, and bright and dark. So this is luminance, and here is when you differentiate between cones trying to make it colored. And here is ocular, so the left eye and right eye. So near the origin, you're trying to make it 2 eyes add together. It's binocular. And away from it, you're trying to, excitatory from one eye, inhibitory from the other eye. So there's a color difference between the 2 eyes. You're trying to see stereo, because only the difference between eyes you can see 3D. Okay? Only difference between cones you can see color. Only difference between time you can see change. Only difference between space you can see, the boundary between one object to another. Yeah? And so information is always in a difference. If it's all uniform the same, there's no information, okay? And so they say, you can have information tuning in color, you have information tuning in space or time, you can information tuning to depth, but can you combine them? Yeah, you have shown me some examples where you can combine. You can tune to space and tune to different eyes. You can tune to space and tune to different color. Here you tune to space but not tune to color. Things like that, remember? And now let's look at what about tuning to these things all together. So the idea is the more you go away from the origin, the more difference you're trying to get. You're trying to get space-time difference. You're trying to get different eye difference. You're trying to get different color difference. The more difference you get, the weaker the signal. Why is that? Okay? The reason is visual inputs are correlated. Remember, say if a 2 pixels are next to each other, they are likely to have the same brightness. Okay? And if red and green are correlated because they cover more or less the same frequency wavelength spectrum. The 2 eyes are correlated. If you left eye and right eye see more or less the same thing. So therefore, they are so correlated that if you want to get that difference, you subtract a lot of commonness away. The difference is always very small. So you can afford to get a spatial difference only by summing over time. You can afford to, but if you try to get all difference, the signal will be too small. Okay? Because of the redundancy, exactly. Because spatial redundancy, temporal redundancy, color redundancy, and 2-eye redundancy, if you try to get a difference, you are getting signal too small. And when the signal is too small, remember our G function, remember, goes like this. There's always the high signal here and low signal here. Low signal here. And we always go from high to low. And our G function is like going like this and going like that. So when you go too small, it simply just dies away, nothing left. Okay? And so therefore, if you want to have multiple dimensions and trying to be tuned to all of them, then you don't have these V1 cells. Okay? And that's indeed the case. Few neurons in V1 are tuned to triple features across all these dimensions. Yeah, and that's the idea. So for example, you can have, this is space and colored, but you can make it flicker. That means not only spatially different from each other, but also color different and time different from each other. When they flicker very slow, you can see changing. What does that mean, flicker? Is at one moment, this is red, that's green. Another moment, that's red, this green. You can see the change. But once it flicker beyond certain frequency, you just don't see it anymore. Basically, your cell got lost. Okay? And this is a demo. If somebody can show it, basically because there's no cell, there's no V1 cell tuned to it. Yeah? I'm not sure whether I can find this demo, but I'll find this demo, maybe put on a link, yeah, somewhere on internet. You can you can make this. Or somebody can even program it by your Python. Just program it by a Python like this, and then try to change in time, okay? And then we can share. And you change in time, so you change in 1 second each, frequency 1 hertz, 2 hertz. You say which frequency hertz, you can't see it anymore. And then trying to make it black and white, you can still see it. But if it's red and green, you can't see it.
It changes the frequency of the food.
Yeah. You just basically make a checkerboard. You can make a checkerboard between black and white. You can flicker with very high frequency. You can still see the difference. But if you make a check frequency of red and green, but try to make sure this red and this green has no difference in brightness. Otherwise, you are using luminous channel. Okay? So if you keep on seeing it, you say, oh, I flicker, still see it. That perhaps means your red and green is not quite balanced. So everybody has a red-green balance spot where you flicker, you cannot see it anymore. This is actually a quite interesting demo. If you can find that demo or program yourself, you can play with it. Quite nice. It's easy to program in Python like that, yeah? Okay, as something fun. Yeah, so this is interesting, and we still have quite some time, yeah? So how can the efficient coding go? So we have another 20 minutes or so, 25 minutes. In fact, we started 5 minutes late, so we could, but I try not to be late, yeah? And so is this a good news or bad news? Usually when a theory comes to an end, you can say the theory still is useful before that, and hopefully motivating a new theory afterwards, yeah? And but before we give up, let's go back to our fundamental. Ask the question of efficient coding, yeah, is this a very good approximation? Maybe V1 is no longer linear, and we assume it's Gaussian. Maybe this assumption, just because you want an analytical solution, it's a very bad approximation, let's say, okay? And is this a good way to write your optimization function? You can say, maybe that's why. Okay, so people then trying to say, let's say, don't have your Gaussian assumption. Okay, give up your analytical solution. Then try to use true images with its true statistics of probability, and use numerical solution, just like many of you do machine learning, gradient descent, trying to do gradient descent in this energy function to see what kind of a filter K you can get. Okay? Doesn't work. Okay? It's still, so therefore, the Gaussian approximation is not a culprit. And I'll dig deeper into that. And then people say, I kind of already mentioned that you can change this function by, rather than writing mutual information, write something similar, but it's a different functional form. Also doesn't work. Okay? And let's try to dig into further, because a lot of you are doing statistical mechanics. You are comfortable with this formulation. So let's see what we mean by higher order statistics. When you do Gaussian approximation, you're writing this probability distribution as just quadratic between two components of our input, Si and Sj, by its correlation matrix. This is called second order statistics. Yeah? You can have higher order statistics. Okay, so you say, okay, my probability distribution of my vector S is something like an exponential, okay, not quite equal sign, but something exponential of Si, Sj, something. That's the second order. But you can also have something, Si squared, Sj squared. That will be the fourth order, yeah? You can also have something Si, Sj, Sk, third order. And you just keep on going. You can just keep on expanding. Things will get difficult. Analytical solution will be difficult. But let's do some exercise about this. Let's try to see what do you mean by, let's try to investigate this question. Yeah, even though, yeah. So therefore, here you have an original image, and I try to make it such that there's no noise. Okay? Why do I want to make it there's no noise? Yeah, so that it's not contaminated by noise, and also you can actually get really scale invariant in that. But that's a different question. And then we do whitening. The whitening is when you have this curve, remember this curve, when you hit the noise, you have to drop. But before you hit the noise, you can pretend that nothing, let's say your highest frequency here, the low frequency is here, and high frequency is here, you never quite hit the noise. And this range is called whitening. You can really get scale invariance. Remember, this is a power law range, okay? And that's called whitening. So you get your filter, really sharp, nice center surround resistor field. You filter that out, and that's your result. Beautiful, no noise. So now you know all these pixels are decorrelated with each other. Okay, there's no noise. They're completely decorrelated with each other. Do you still see object in it? No? You see the peppers and all these kinds of things. Maybe we should close the curtains. Otherwise, they're a bit too bright and people do not. Some people are shaking their hand. Can you see in the back? Yeah? Or maybe you look at this. Yeah? Okay. Maybe we can close the curtains so then it's not too, people can see the object. Because how do we close the curtains, no? There's something, there is a string here. Okay. Great. This curtain closed, you can hopefully see the images. Okay. Maybe it's better? Now can you see in the back? Very good, okay. So the peppers and things still there. Even though the pixel completely decorrelated, because we actually decorrelate all the way to the fullest frequency, okay? So the second order redundancy have completely removed. Individual pixels should be independent if they are completely Gaussian. The fact that if it's completely, they don't look like a noise to you. So therefore, things are indeed not Gaussian. Yeah? Otherwise, you would not be able to see your objects, no? Obviously, there's some structure in it. Okay? Great. Now we really turn it down, and your resistor field gets a bit bigger, okay, because it's a dimmer environment. But then you can accumulate, bigger, then you actually see this. So that means these pixels, even though it's no longer second order correlated, there must be higher order information in it so that you can see the object. If there's no higher order information, they were just like a salt and pepper noise on your television channel when, when the signal is plugged, yeah? Okay? Unplugged. So let's investigate exactly in what sense that one output node O1 and another output O2 are their joint probability distribution. Their joint probability distribution looks like indeed it's independent, yeah? What signal O1 is and what signal O2, they're all kind of near zero Gaussian-like thing. And this middle is zero, okay? Negative O1, positive O1, negative O2, positive O2. Well, looks like, and I make a log so that I can have very high probability, low probability. I will point it out. Looks like it's independent. Well, but turns out that we can also use these kind of quantities. If you are truly Gaussian, then the fourth order, this quantity and that quantity should be equal to 3 for true zero mean Gaussians. And if they are indeed two signals are zero mean Gaussian uncorrelated, then this should be equal to 1. Okay? Let's put the O1, O2. Okay. So is that really true? You find that in this O1, O2, they are not truly Gaussian, but they are kind of going like this. But nevertheless, because this is log, these are very low probability events, okay? Because I put log here. So for low probability events, they are not Gaussian. In particular, the kurtosis is not 3, it's 12.7. It's actually quite different. Okay? And also, if you plot another way, which is a conditional probability of O2 given O1, and such that you normalize because it's a conditional probability, then you see that they are not independent. These are really, O1 and O2 are not independent. So at this O1 place, O2 are very near 0, but at this O1 place, O2 is completely spread out. So therefore, O1, O2 are not independent, but in the higher order dependency. Okay, in particular, this value is 5.1, but if it's truly Gaussian, it should be only equal to 1. So you may say maybe Gaussian approximation is no good. However, we are actually quantifying things by these entropy-like stuff. So let's also do the entropy thing. So how much redundancy is in the higher order statistic in terms of entropy? Okay. So let's do it by after quantizing S or O into 64 equalized sized bins, okay, the equalized discrete things. And you find that you find that the one pixel, each pixel's entropy is 3.4 bits. But the joint entropy is 6.64 bits for 2 pixels. If they are indeedly completely O1 and O2 are not correlated, then this should be equal to twice of that, right? Is this equal to twice of that? Almost, yeah? Almost. So you can find the redundancy. Redundancy is this, and it's less than 3%. So therefore, if you do not measure by kurtosis or this quantity, you measure by entropy, the redundancy is tiny. So if that's the case, Gaussian approximation is quite good. Yeah? So it's a different point of view. Now let's recall that in the first efficient coding lecture on Tuesday, we're also trying to calculate redundancy in the original image. Okay, so that's why I also discrete S into 64 equal size bins. So it's completely equivalent. Then you find in the original image, you actually get 5.64 bits, almost 6 bits, yeah? Because 64, 2 to the 6 is equal to 64. So if you 64 discrete levels completely equally distributed, then you will get actually 6 bits, so 5.6 almost. Okay, this is the original thing. And if you take 2 neighboring bits, neighboring pixels, it's 7.58, not far away from 2 times that, yeah? And the redundancy is almost 50%. So therefore, the original image redundancy 50%. After you remove the second order redundancy, second order correlation, it went to only 3%. So that means Gaussian approximation quite good. It just removed most of the redundancy, yeah? Only leaving a little bit not left. So redundancy in higher order statistics is relatively negligible. And then you can ask the question, is it worth expanding V1 by 100 times just to remove the last bit of redundancy? That's a question we can ask. Maybe the brain really want to do that? Okay. And it's worth expanding 100 times resources. Remember, the brain costs a lot of energy. That's one question you can ask. Another is, this is trying to remove all higher order redundancy. How do you do that? You take this image to the Fourier transform, and then randomizing all the faces of your Fourier components, and do the inverse Fourier transform. Then these two have exactly the same first and second order correlations. Okay, these two images. This has, can you see the salt, pepper in here? No peppers. So that means the first and second order correlations do not tell you much about object. It's the higher order statistics that tell you about objects. So if you remove these redundancies there, you will not be able to see the objects anymore. So the brain is actually trying to see the objects. So you should not try to remove the last 3% of redundancy. If you remove them, you can't see objects anymore. Okay? So there's two reasons not to remove these higher order redundancies, because they are where the objects are. And also, it's only tiny little redundancy compared to the first and second order redundancy, okay? And so this is a very good reason that the brain is actually trying to keep this. Because imagine, this is a long line, yeah? This is a long border, and this long border cannot be just second order redundancy, yeah? This is really high order correlation between this pixel and that pixel, between this pixel and that pixel. It's 3 pixel correlation, 4 pixel correlation. This is really high order, okay? You know, if you look at this, the border between this book and the blackboard, you know, you basically look at objects through its contours. The contours are really higher order correlations in space. And you actually want to keep it in order to recognize objects, yeah? And so therefore, this is very a point to keep in mind. And so therefore, even though we have problems of understanding V1s through efficient coding, maybe it's time to think beyond efficient coding, okay? Beyond efficient coding. So what are the beyond efficient coding? Well, maybe we do want to think about translation and scale invariance, even though, yeah, that's actually beyond efficient coding. And another thing is, so far, we always talk about information as the number of bits, We have never talked about the meaning of information, yeah? You know, what is the person, you know, what the word says. And the meaning of information is not in the information theory. The information theory talk about mutual information. It's just the quantity of information. They are two different things. So to go to meanings, maybe we cannot process all the meanings. So you have to select which part of the input you want to process. So you have something on information selection. Some meanings are more important to you, such as food and predators, and other meanings are useless for you. You should delete. Because otherwise your brain will be too tired to process all information, yeah? So for instance, when you look at me, do you try to count how many eyelashes I have? No. You're just trying to see whether this is, you know, one person versus another person. You are not trying to see all these meaningless things about the eyelashes, no? Okay? So therefore, you need to select meaningful information to process. That's called attention. In psychology, but it's not very clearly defined in psychology. But in information-wise, then you can say attentional selection. So it's more clearly defined, which is something a theorist like to do. Therefore, it can make more progress. Yeah, and we are going to start tomorrow with information selection. Okay? And, yeah.
I didn't understand that when we are processing a picture,
Yeah.
how does the brain find out that which redundant information is necessary to be kept and which are not?
Yeah, actually, I don't know how the brain, yeah.
Or, for example, in my theory, in our
Yeah.
model,
Yeah.
How can we find out that which redundant information are necessary to be kept? Or which
Yeah, there.
is better to
Okay. I do not know how the brain find out that this whitening is just enough and kept some useful information for us. Yeah. Somehow when we do this Gaussian approximation, it says, you know, another thing is that maybe the brain thinks that linear stuff is easy to do engineering-wise, and then just did it in evolution. And with this doing it, it turns out that it's very useful, and it kept it. I don't know. That could be the reason. Do you see what I mean? And so you have one neuron to another neuron, use these linear transmissions, because this is trying to use linear transmission from S to O. Maybe this is one of the evolutionary genetic random fluctuation that did it. And once they did it, it turns out it's a good thing. You know, I also skipped the part that how can the brain learn to do it? And that you can also find in my video, or, well, actually, it's not quite in my video. It's a little bit in my video, but in the book, you can also find. This is something out of our solution, but the brain does not solve equations. It's just a little bit random, you know, this kind of a plasticity. Yeah, it could do it. Remember I said you go from outdoor to indoor, the brain has a mechanism, change your resistive field, okay? It can do it.
But when we are trying to do that, I mean, in our model, we know actually consciously, yes. For example, we know that here are the bulk of the body, and we can throw away the redundant information. But for example, in the border, these redundant information are important.
You can say this is how we can understand this data, understand this phenomena. The brain probably bumped into it by accident. Those species didn't do it, died out. So we lived because we happened to hit this right solution. So how the brain figured out this, I do not have answer. Yeah, and now that the brain is like this, we as experimentalists who are biologists so far, but we physicists could do that as well, to measure the resistive field, then trying to understand this efficient coding is one way of getting it, and then we hit the wall and say you could not get further. Then another question,
this
yeah.
whitening depends on the distribution of neurons in the brain biologically.
Say it again?
This whitening
Yeah.
in the brain
Yeah.
depends on the biological distribution. Biologically, it depends on the distribution of neurons.
Yes, the whitening is the center surround resistive field in the extreme case of no noise. Yeah,
The
yeah.
coefficient in the brain depends on the interaction between neurons.
In the retina, it does not depend on the interaction between neurons.
The processing, how the brain processes this information.
How does the brain process this? Is by the resistive field?
Exactly.
Yeah. By the resistive field of K. K is doing the right whitening. Yeah.
I mean because like in biology, if you
Yeah.
have
Sorry.
if you have a colony of bacteria, put it in a dish with food, it always finds the the most optimized way to distribute itself to eat. Like this is experiment when they did it. I think in the it was like they was trying to model the Tokyo subsystem, something like that, by bacteria, and they found that the bacteria distribute itself by the most optimized way. So I think the brain did the same, maybe, like it distributes itself biologically.
Biologically, you mean how does the brain find the best K?
Exactly.
Is that your question? Yeah. Well, it turns out that I am not sure. So in the book, there is a developmental algorithm. You can also kind of find it in one of the videos. Okay, in one of the video efficient coding, it has. So the idea is, it has like a O1, O2, O3, and then the S1, S2, S3, and how this goes up, and then maybe they can talk to each other. You have put certain called learning rules. So in computational neuroscience, you can have certain learning rules. And there is a particular learning rule where it depends only on local interactions. And that will get your whitening solution. However, non-whitening solution, how does it get it? I do not know. That is, unfortunately, because normal situation, you always have some noise. It's not exactly whitening. Only when this noise is zero, it's exactly whitening. But the brain must find a solution to get it, which the efficient coding doesn't quite cover. Yeah, okay. Efficient coding theory, it just tells you what should be the best K, but does not tell you how to get it by biologically plausible mechanism. Currently, we are doing it by mathematical derivation, which is not a biological plausible way, because the brain is not trying to do derivation like a PhD student is trying to do. Yeah, so that's the idea. We're trying to, but nevertheless, And so now let's try to evaluate. Okay, so this is something I like to kind of do for every theory. We're trying to do some evaluation. You can say, how do we choose this theory to teach? First of all, teaching our course. First of all, we choose theory that should link visual behavior with neural basis. So if you have a theory and model, you should say something about the neurons. okay? And you should also say something about behavior, which is intelligent, yeah? I can recognize you even when you get closer, further, going, and you turn around, I still see the same person. So very intelligent invariance. This is called object invariance behavior. There's a symmetry in there. It's very clever, yeah? And so we do not want models. We do not, so I kind of narrow down what theories to teach. They have to tell us some neurons. So efficient coding theory, does this tell us about neurons? Yes, it tells us about residual field. Yeah, so satisfy that. Does it tell us about perception and behavior? Yes, now we see why sometimes we can see color, sometimes we don't see color, why sometimes we can see motion well, sometimes not, yeah? So therefore, this theory satisfies this requirement, okay? And that's why one of the reasons. And secondly, it needs to be falsifiable. That means it has to have a prediction that you didn't know before, that you can do experiment and test it, yeah? And so should have prediction that can be experimented and tested, and we do have an example in the first day when we show how that you can give people exactly the same image and then, they change, yeah? And did you do this game of, dropping things and catching it? And that's one of those predictions, yeah? Yesterday when I make you do it, maybe I should have make it higher, so take more time for you to catch it, yeah? You find a place to catch it and then turn off the light and suddenly you cannot catch it. That's something you can test, yeah? Okay? So, and the prediction should not be too trivial, otherwise you can predict, and yesterday it didn't rain, today I didn't rain either. Tomorrow will not rain. Okay, so that's just an extrapolation of knowledge, and also does not quite distinguish your theory from another theory, because another theory predicts the same thing, and then you cannot distinguish the theory. So that trivial predictions cannot distinguish between theories, and almost like you don't need a theory, you can predict it too. That you should also not have. And so in this case, this theory is non-trivial and can have predictions. And we would prefer a theory that already has at least one prediction tested. Otherwise, we will also have too many to maybe teach. Yeah, some predictions not quite tested, and who knows, then the material will be too much. And that's how we do that. So efficient coding theory satisfies this requirement, and that's why we put it into this course. And starting from tomorrow, we are going to meet the frontier where the efficient coding makes us puzzles. That's V1. And let's try to understand. And you can imagine the next thing we're trying to go will be selection. So the information comes in, you need to select a little bit to be recognized. So that's it. Yeah, okay. See you then tomorrow. And you can understand this more by doing a little bit of homework or watching a little bit of video and so on. And the TA has a lot of these. And I'm trying to put this slide as a PDF file to upload to the website.